Hi everybody, in this video we are going to be learning a comprehensive guide to distinguish acids from bases and strong acids from weak acids, and also to determine neutral substances, and we will go over some other things as well. But with no further ado, let's begin. So, the first thing we're going to do is talk about strong acids. These are acids that completely dissociate into H pluses, or as we just learned, the reality of it is that strong acids will almost completely, which is indicated by this approximate sign, they will 100% ionize, which means that they'll completely or almost completely react with water to form hydronium ions, which is our indicator of acidity, as we learned in the previous video when we talked about pH. So here are the strong acids that you must memorize. Sorry, but there's a little memorization, but I promise you it's not too bad. The first group of strong acids we will memorize are called the halogen acids. They're called halogen acids because the acids have halogens in them. So we have, actually, pause the video and see if you can name these 7 acids. Alright, I'm assuming you were able to, and if not, here's a little refresher. This one's hydrochloric acid, this one's hydrobromic acid, and this one's hydroiodic acid. And then we go to these acids. They have chlorines in them, but they're a bit different from hydrochloric acid. We have chloric acid and perchloric acid. And then we have these two acids. These two are particularly useful, and they're used pretty often. So we have nitric acid and sulfuric acid. Those are the strong acids that you're expected to memorize because they'll help us distinguish between strong acids, because as we'll see later, anything that's, well, anything that's not on this list is going to be a weak acid typically. So that's what this box says. Now, before we go on to the next box, let's talk about other ways to determine strong acids. So, there's a logic component which we discussed in 12.2. The conjugate acid of a neutral or non-basic substance is always a strong acid. And this goes back to the idea that we talked about how a very weak base will produce a very strong acid as its, conjugate. And when I mean very weak, I typically mean neutral. So what does neutral mean? Well, as a little, I guess, brief introduction, the neutral substances you should be aware of are water, methane, and any hydrocarbons, since they behave like methane but are bigger. Now we also have the conjugate bases of strong acids, since the conjugate of strong things is always very weak or neutral, as we just said. So we have these strong acids, right? So the conjugate bases of them will be neutral. So we have chlorine, bromine, I mean chloride, bromide, iodide, chlorate, no, this is perchlorate, chlorate, nitrate, and we have an exception here. We have HSO4 minus. This is actually not going to be neutral. It's going to be acidic because of the H that it has. All of these guys don't have H's, but this one does. So it's an exception to our rules. And that's, basically how you determine what strong acids are. So as an example, CH4 is a neutral substance. So its conjugate acid, so how do we make a conjugate acid? Well, we're going to add a hydrogen to it and make it positively charged. So this is a conjugate acid, and as you can see, it's pretty unstable if you draw its Lewis structure. So it's going to be highly reactive, and that's why this is actually going to be a strong acid. So that's just an example of how the logic component is used, but you'll normally see these as your strong acids. So up next we have weak acids. Weak acids are acids that don't react completely with water to form hydronium ions. So as we said before, usually anything that's not here, or basically anything that's not a strong acid, it's going to be a weak acid. Some examples are, this is called acetic acid, which is in vinegar, hydrofluoric acid, that's super dangerous, and we have ammonium, which is an ion. Now, we have a few more weak acids, so let's look at the logic component of how we determine what a weak acid is. So, the conjugate acid of a weak base is a weak acid. So, what is a weak base? Well, a weak base is something like F minus, and you see its conjugate acid is this, and they're both weak. So weak is weak, and we talked about this in the 12.2 video, so if you want to listen to me talk about it, I guess go back to that video. Now, we have some ions that we have to memorize that are going to be acidic. So these are actually conjugate bases of certain acids, but they're going to be acidic because of the H's that they contain, since they can still give off H's. So they are still technically a bit acidic. So this is called the bisulfate ion, or hydrogen sulfate, whatever you want to call it, and this is dihydrogen phosphate. Alright, we have other weak acids, so metal ions are actually weak acids. And why is that? Well, let's take a look at a metal ion like aluminum. So the aluminum ion in water will form a hydrated form of the ion, because water likes attaching to positive things because the oxygen is partially negative since water is polarized. So naturally it will form this complex ion, the hydrated aluminum ion, and this is an example of a complex ion, as I just said. So this complex ion will have a +3 charge, and it will actually react with water, because remember, water likes positively charged things, and it'll do a acid-base reaction to form the products, which is a hydronium ion, and also this, which is also a complex ion, but one of the waters have been replaced by a hydroxide, which is this OH over here. Now note that this is not a complete reaction, it has the equilibrium signs, and it's a weak acid because it's not going to go completely. Like, not all of these are going to react with water. Only some of them will. And in 12.1, we talked about Lewis acids and bases. So this is a really, I guess, comprehensive review of that. So this aluminum will be surrounded by 6 waters, and these 6 waters each have, 2 lone pairs, but each water is going to donate 1 lone pair to form a coordinate covalent bond. So, a bond is 2 electrons. So it basically changes these 2 electrons into a bond. So that's what we see over here. All the waters are connected like that. And you can see that overall it's still a +3 charge. So there you go. And it's going to react with water now. So this is where the water comes in. It's going to do a Lewis acid base reaction. This is going to be the Lewis. Let's see, it's donating the electron, so it's the Lewis base, and the electron acceptor is the Lewis acid. So this is our Lewis acid, and this is the Lewis base. Simple enough. It donates the lone pair, and this lone pair gets clumped up here, and now we have this happening. This is our hydroxide group, because now, it has 2 lone pairs instead of 1, because this hydrogen donated the single bond into this oxygen, and this H2O just, took this H and kind of, attached it to itself. So that's why we have an H2O. And you see how this lone pair turned into a bond and attached to the H? That's just what happened. And this is kind of a review of, video 12.1. So if you're confused, go back to that. And in the end, we have hydronium, and we have this. Now it's 2 plus now, for a lot of reasons, but most basically, it's because um, of charge conservation. So if we have a +3 here, and we know that hydronium is +1, then this must be +2, because both sides should have the same charge at the end, because charge should be conserved before and after a reaction. That's just how it works. Alright, well, let's talk about one more thing. The higher the charge, the higher the acidity of the ion, and this is because we know that this lone pair are, they're electrons. They like positive things. So the more positive this number is, the more likely it's going to react. And the more likely this reacts, the more, hydronium it is going to produce. And that makes it more acidic. So higher the charge, higher the acidity. Now let's move on. Let's talk about our strong bases. So all salts containing OH minus is a strong base. And I forgot to mention this, but we have a convention. Anything that's as strong or stronger than hydroxide is going to be a strong base, and anything weaker than hydroxide is a weak base. And over here, we have a convention where anything stronger or equal to hydronium is going to be a strong acid, and anything that's weaker than hydronium is going to be a weak acid. Now you might be confused, because you don't think this is an acid, but it actually is, because it can donate hydrogens. But we'll talk more about this when we talk about acid-base equilibrium, because we will soon have to figure out, which one's going to be the stronger acid based on their pKa values and stuff like that. But let's not worry about that for now, but just keep that in the back of your mind, that H3O plus is actually acidic. And yeah, I mean, it is the conjugate acid, after all, of water, right? So it is an acid. So remember that. And this is the conjugate base of water. That's interesting, right? All right. So we disregard solubility. So for example, we might have learned that magnesium hydroxide is not very soluble, but it's still a strong base, because when we look at strong bases, all we care about is the base that's inside. Remember, magnesium is just an ion. It won't do anything. It's the base that we care about. Oh, well, we just learned that this might be a bit acidic, but, it's not. It's a weak acid, and this is a strong base. So overall, the salt is going to be very basic. So this is our strong base, OH minus, and as long as the salt has OH minus, regardless of solubility, it's going to be a strong base, because technically, all the stuff that actually dissolves, even if it's just a little, that stuff's going to be super strong because it has that OH, and OH is a very strong base. Now let's look at the logic. The conjugate base of non-acids or neutral, compounds is going to be strong. So let's take CH4 as our neutral substance. Look at the conjugate base, which is you remove an H and you put a minus sign. So, this is going to be a strong base. There you go. It's actually going to be stronger than OH minus, but that's beyond the scope of this, video. It's just a fun fact, but this is a strong base. It's very unstable, unhappy, and wants to react, and the more something wants to react, the more likely it is going to be a base. Now let's talk about weak bases. The common ones are ammonia, water, and some other stuff. So here's a box that says that anions will be weak bases. So like the conjugate base of a weak acid is going to usually form anions. So there are a few exceptions, like, these two. These two are conjugate bases, but they're acidic because they have, that H. But some things that contain H's are actually basic, and they're the ones that I haven't talked about yet. For example, this is carbonic acid. Its conjugate base is going to be bicarbonate, and this is going to be basic because it's going to like to accept an H, right? And yeah, let's talk about amphoterism now. An amphoteric substance can behave as an acid and a base. So we just mentioned HCO3 minus. This is basic, but it can act as an acid as well because it can donate that H plus, right? Or it can accept an H plus to form, carbonic acid. We have a few others. We have dihydrogen phosphate and biphosphate, or hydrogen phosphate. We have water. Now water can act as an acid and a base because it can form these two, right? If something has both a conjugate acid and a conjugate base, it's going to be amphoteric, and this one is going to be too. This one's going to have NH2 minus and NH4 plus, right? Awesome. So let's talk about the conditions for amphoterism. So it needs to have an H in it, or else it can't be an acid. It should be at least acidic or basic. So, for example, methane is neither acidic nor basic. So we don't consider it as an amphoteric substance, even though it could be, but it doesn't react like that. So since it's neither acidic nor basic. Now water, in this case, it can be both acidic and basic, and we see it in reactions all the time. When we do neutralize, or when we look at the reactions between a strong acid and water, water is technically acting as, the base. So it can act as both an acid and a base, but usually methane doesn't do that because it's very non-reactive in the sense that it doesn't react as an acid or base. Instead, you see it more in combustion reactions. So we don't usually consider non-reactive substances, when I mean non-reactive, I mean things that don't act as acids or bases. So these things will typically not be considered amphoteric. Now, you should not be strong. So something like HCl, I mean, it's going to be an acid. I mean, yeah, it could accept another H, I guess, but we don't usually consider strong things to be amphoteric. So there's a little recap of that. And now let's tease ourselves by talking about oxides. We're not going to go too deep into it because it gets kind of complicated, to be honest. But basically, metal oxides are basic. So something like this reacting with water will form hydroxide. So the oxide will form the hydroxide. And then we have non-metal oxides. They're acidic because they react with water to form acids. And as you can see, usually you just combine the two to form the third. But in this case, we have like this. We have tetraphosphorus decoxide. I don't know. I think it's just phosphorus oxide, but this will react with water to form phosphoric acid. And, basically, you can't really tell what this is going to form. You just know that it's going to form an acid with O's in it. So usually non-metal oxides will form oxoacids. They're acids that contain oxygen because they have to react with water, and water contains O. So it should have an O in the final product, which is why that they typically produce oxoacids. These two are oxoacids. Another oxoacid, well, all these are oxoacids actually. But yeah, this is a very, I guess, quick overview of acids and bases, and hopefully you will be able to determine what is a strong, weak, acid, or base, and what are things that are neutral. But don't worry too much about it because it's complicated. It gets more complicated when you have to compare two acids and tell which one's stronger, which one's weaker. But we're not going to complicate ourselves. All we care about in this video is recognizing these acids and bases and whether they're strong or weak. So I guess that's all for this video. Thanks for watching this chaotic video. I made a lot of mistakes, but it's okay. Everybody makes mistakes. Life lesson learned. Yeah, have a nice day.